Hello, everybody, and welcome to another episode of Zed Decoded. Today, I have with me on my right and his left, Antonio. Welcome, Antonio.
Hey everyone.
And what we're doing today is we're going to optimize our rope data structure. So last week, I think it was it was last week. So last week, Antonio already did some optimizations on the rope data structure, which we also made an episode about like a couple months back. And I was scrolling through the diff and realized that he was up to some really interesting stuff, right? There's a lot of it looks normal up here, but then you get down here and then you find this kind of code. And he got my curiosity with this. So today we're going to follow up on this and maybe add another optimization. And this episode will just be the two of us pairing on Zed, basically. But maybe we can start off and you can, I don't know, give us like maybe explain in rough terms what you did in this PR.
Yeah. I think it might be worth just recapping what a
Yeah.
rope is in Zed. Like it takes advantage of that data structure that we've talked about in a past episode, which is the sum tree, which basically
Yep.
lets you lets you store a sequence of items. The items can be anything, and then those items can be summarized and will be summarized up a B tree, and that's used to kind of index into the sequence and very easily perform translation from offsets to points to character UTF-16 characters and whatnot. And so like you can see here, that's showcased here. A rope is just like a sum tree of chunks. And so yeah, in the past, all we had in the chunk was basically this array string, and array string is just a string that's stored on the stack. It's not heap allocated, and yeah, it has. I guess yeah, the invariant of the rope is that it's this. Each chunk is between min base and max base, which in release mode it means like that each chunk is between 64 and 128 bytes. So that's the way it was before.
So that means there was no, on the level of the chunk, there was no indexing. Like if I
Exactly.
had to ask the rope, the rope, I ask you like, where's the new line? The rope might have indexed this,
Correct.
right?
Yeah.
But then once it could only say there is a new line in this chunk, but it couldn't
Correct.
say where in those 128
Correct.
bytes.
If you
Okay.
look, this is the sort of the high level code that does it. Like notice how at the rope level we say, okay, we want to sort of create a cursor on the chunks, which is that sum tree I showed before, and we want to kind of track usize and points. So like we're going to seek in terms of like bytes, but we also want to track where we are in terms of points. And so, that lets us very quickly identify, we seek to that offset, and that lets us very quickly identify a chunk that contains that offset, like you said. But then we reach that chunk and now we have a whole 128 bytes potentially to kind of visit and understand, where is that line, right? Where's that point in terms of, the offset that we passed in.
Yep.
And so yeah, like basically the gist of that PR was that we can index more information at the chunk level by densely packing kind of various kinds of information into a bitmap essentially. And so it's this like I said, the chunk is going to be between 64 and 128 bytes. So we have each chunk now contains, for example, this new lines field, which is now we have like 128 bits to say, okay, at this location in the string, we have a new line.
Okay, so you have a bit mask, right? Like,
Exactly.
and this, ugh,
Yeah, say that. Yeah.
128 of these slots, right?
So say that
Or
we have this, right?
yeah, you have an
Like the
LOR.
and maybe sorry, let's have multiple new lines there.
Yeah.
So you can imagine sort of like the new lines bit mask saying, okay, like at this location, we don't have a new line, no new line, no new line, no new line, no new line. Oh, here we have a new line, right?
Yeah.
No, okay. And then, no, 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 blah, 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 blah. And then,
Oh,
yes, we
then you
have it.
have one. Yep.
And so like this lets us very quickly using, bit manipulation, sort of address these new lines in the string. Like, so for example, a really cool and easy one that we did. So we were looking offset 2 point, right? I think
Yeah.
so, yeah. So here we need to take extra care to sort of like make sure that if they use an offset that is the max base, we don't kind of overflow with the shift
So,
because that's undefined behavior. Oh, go ahead.
so to interject, right? A point is, like you can see here on my screen now, it's a row and a column. And in order to translate from an offset, which is the byte offset in a string, you need to count the rows. You need to count the lines, which is exactly what we were talking about.
Correct.
Right?
Correct. And so, what we could do here is basically say, ignoring this if, which I'm only doing because, yeah, if you shift by 128, it's a panic in Rust. But anyway, like, notice what I'm doing here. I'm kind of taking 1 bit, right? So like the word one, I guess it's not a word. It's like, yeah, 2 times the word. So yeah, I'm taking this basically. Imagine like a bunch of, you know, bits there, and like I'm taking that one and I'm shifting it by the offset. So say that we want to shift, the offset is 5. So what we're gonna do is we're gonna say, help me count to 5 here. I guess it's like
1, 2, 3.
it's gonna be here, I think, right? Because we shift it, so it will be, 1, 2,
Yeah, by
3,
if you
4,
shift
5.
by 5. Yeah.
It's gonna be there, and so that's basically what what we're doing there. And then like what we do is like subtract 1. The effect of subtracting 1 is that we're gonna kind of null out this 1 to a 0, and all of these are gonna become 1s. So basically we're creating like a mask that ensures that up until that offset, we can kind of, all those bits are gonna be flipped to true, right? Okay, now we have that mask. Now we take that mask and kind of end it with the new lines. So now imagine like this is basically a way of saying, okay, count just the new lines between 0 and the offset, right? Like we're just kind of opting into just those new lines. And then we
So
can say, oh, go ahead.
so we have the offset, right? The offset is relative to this chunk,
To
right?
the
And we
start of the
want,
chunk, that's
yeah,
right.
so we want to say at position 5 or whatever it is there a new line, right? So we take the offset, right? And we end up with this thing here, and then we do subtract 1. So now our mask, like this value here, is this, right?
Correct.
So now we want to use this to figure out whether at this position there's a new line,
Not
right?
exactly. No, what we want to know
Okay.
is like how many new lines are between 0 and that offset. In
Right.
fact, no, yeah, which is
Okay.
slightly different, right? Because like
Yeah.
imagine like we had, so imagine that this is like the new lines, right? And I'm gonna pad this for a moment. And imagine that like we had a new line here, a new line here, no new line here, and a bunch of new lines here. Like we
Yep.
want to know just how many new lines we've got between 0 and the offset that the user asked for, right?
Yes.
Like we don't
Okay.
want to count the other ones. So basically like we're masking the rest of the new lines out so that we can consider just this trailing part of or leading, I
Yeah.
guess, of the new lines. And then we use count ones, which in modern architectures is just like one instruction. It's pop count. So yeah, that gives us the row, right? Because like, we can count how many new, if we can
Then
count how
gives
many
us this,
ones.
right? It says
So we
well
null
this
those out, exactly. And now we can count how many ones we've got
yeah.
there. And if it's like, if we got 2 ones,
Then there's 2 new lines in
there's
that
2, right? So like, we're going to
up
be
to
at
that
row 2.
offset.
Right. And then what we do is like, we sort of say, okay, we know where the last new line was. Like this lets us understand the index of the last new line. And with that, we can calculate the column. So it's basically like how many bytes we're calculating, how many bytes since the start of the row do we have? And that's our column. And that, yeah, basically like in constant time, we can figure out,
Yeah.
where there's this offset in the chunk.
Man, so little code, and yet it's crazy.
It's pretty cool. I mean, yeah, and I don't know. Yeah, so basically, like, it's taking advantage of all of this stuff. So the new lines is one piece of information that we index. But yeah, we index more, like, because we need to perform other kinds of translation, right? Like we need to
Yeah.
know, where is it? Point 12. I mean, yeah, here we go the other direction. But for example, sometimes we want to convert from a UTF-8 offset to a UTF-16 offset. And even here, like, yeah, we kind of use these masks to our advantage because we know exactly where the UTF-16 characters start, and we know, we can basically count, like translate from UTF-8 to UTF-16 just by like in constant time again by using like bit
So
manipulation.
what does this contain, the chars UTF-16? Is this like a bitmask that contains the start?
Yeah, let's see how these are populated. So if you look at how we create a chunk, sorry, let me go back here. Well, it starts with just, default empty, and then we push. So basically, like, you can mutate existing chunks because, again, like, we want to be able to mutate chunks in the rope. But yeah, the thought is that, like, we take the text and, like, sort of iterate over the characters, and this basically lets us track, like, where we have characters as, in terms of, like, UTF, sort of,
16.
no, a Unicode code point. So like we want to
Yeah, yeah,
track
yeah.
both, like, a Unicode code point, which is like, I forget how they call it, but it's like they call it Unicode scalar values. Like it's basically like
Yeah.
a character in Unicode terms. And then like we track where we have a UTF-16 character. So like for each character for each Unicode character in the string, we say, okay, we're going to put a 1 at the location where this character starts. We're going to do the same for UTF-16. And in addition to that, we're going to, like, if the UTF-16 character is like 2 bytes long, because like in UTF-16, it could be either 1 or 2. We're going to say, okay, like we're going to add another bit to count this character sort of twice in UTF-16. So imagine that like this character in UTF-16 is like too long, right? Like it has a count of 2. What we're gonna do is like we're gonna kind of shift this bit to the index where the character started, and when if this is the length UTF-16 is 2, this is means that like we're gonna put a 1 right by it so that we kind of count it twice if the length is 2. And similar story for the new line. So we say, okay, was this character a new line? If so, like we're gonna kind of perform this comparison. This will be 0 or 1 depending on whether like the comparison is true or not. If it's true, this is 1. We're gonna take this 1, shift by where we found this character, and kind of assign it to the new lines.
Nice.
So we do this just the one time, and
And then just for my own understanding, the chars. Wait, so how does this work? Char indices, isn't this always going to be incremented by 1?
no.
The idea is that it's not, right? But
No,
then
because here, like, the chart indices are telling us, okay, this is the index at which the Unicode scalar code point sort of starts. But that could be like up to 4
right.
bytes long
Okay.
in UTF-8, right? So like
okay.
so yeah, we count the character once, the UTF-16 possibly twice in the bit map, and then we just track the new lines. And this is enough information to sort of say, like, in a way, you could imagine the new lines as kind of also telling you where the, they are tracking effectively kind of the UTF-8 locations.
Boundary,
like, so.
Okay, so if you have like emojis in a text and one of those family of firefighters, whatever, like the combination of multiple other emojis where you end up with 4 bytes, then and it would be full of this. The index would be offsets of 4, right? And then
Correct.
you would always leave a 1. Okay,
Right.
and then
Exactly.
UTF-16 works a little bit differently too.
Correct. And so,
Okay.
like, what's very interesting is that, if you want to know, we have this thing where, like, we ask, how many characters do we have in, the first line of the chunk?
Yep.
Well, if we have no new lines, we can just count the ones in that char's bit mask, right?
Mm.
But if we do have new lines, then we want to sort of, um, you know, take notice where in the string like the first new line starts. So like we find the locate. So this trailing 0 tells us, again, constant time tells us where that new line starts. We sort of
Yeah.
like put the bit there, flip it with that -1 trick, and then we know exactly how many chars in that first line we have with a pop count instruction. It's pretty cool.
That's pretty cool. Yeah. I mean, even this, right? Like here, just like get the point representing the number of lines and the length of the last line. Like
Right.
just this, right? Count the ones, give me the leading zeros. There's no branching here. This is
No
just single
branching. This
instruct. Yeah.
is, yeah. This was pretty, yeah.
And for everybody, when we talk about branching, every loop that you have in your program includes a branch, right? Because the condition of a loop is a branch. And
Right.
the problem with branching with modern CPUs is that CPUs do something called speculative execution. So if you have a branch in your code, your CPU thinks, oh, it might be true or it might be false, and it starts to execute both of those. And if it's wrong, like if it goes one or the other, then it kind of has to throw that other result away. But if you don't have any branches, your CPU or CPU cores can go as fast as possible, right?
Correct.
Yeah.
Yeah, so the branch predictor, right, is not executed in that case. We do have conditionals, and like, for example,
Yeah.
here we have this if over here. Although, like, the cool thing about this is that, like, I don't know. I think there's a way of writing this without the conditional. So I don't know how this gets. I didn't look at the assembly, to be fair. Like, this probably gets compiled to like a branchless operation,
Yeah.
probably. Um,
I mean,
yeah.
there's this other thing, right, where there's also a compiler still in play here.
Right.
And if you have like a comparison with 0 thing, maybe it can optimize this to a different
Right.
thing. But still, like if the less branches you have further up, the better the compiler
Correct.
can optimize. Yeah.
And crucially, like you said, this thing is not in a loop. Like I think before, if we wanted to find out what the last line characters was, we needed to go through each character. So that's one loop. And then like we need to track on the side how many new lines have we got up until this point, and blah blah blah. So yeah, I mean, and like we saw in the benchmarks, do you have that PR open?
Yep.
Anyway, yeah, certain things got to like up to 2x faster.
I mean, change, right? Times here. Like,
Push kind of stayed the same. I mean, -3%, because we're not really what we made better is like kind of.
But here, append
indexing, right?
time
Append got better because we're doing less. Yeah, we're doing less in that code path, but also like look at, I guess, slice. Yeah, things where like we index into the rope got a lot faster.
They're here 50% faster. Chars, this counts the number of characters, right?
Yeah, chars is more about, no, it actually iterates.
Oh,
through
it's
characters.
an iterator. Yep.
So that got slightly slower, but I think that's
Yeah, but this is the one you were after, right? Point
exactly.
to offset.
Like clipping and point to offset, they all got, sort of, that's what, 70%? Sorry, the screen sharing is a little...
Sorry, let me bump the font size here. So yeah, 70%. Here, -60%, like 60% faster throughput, a lot. Yep. Oh yeah, that you even said it. Like this got slightly slow, but it's not like it was 5% or something, right?
Yeah, and we don't really call chars for an entire rope. Like it's mostly when we call chars. Right now, we're using it for point translation, which is the thing we're gonna get rid of together as per this. But yeah. So
this is pretty impressive numbers, though. For you would think that in the grand scheme of things, like just a few bits and bytes, but it does like end up if this is your central data structure, right?
Totally,
and I mean, just I think that was previously in this file, right? And just to see, the chunk was in here. Offset to point. There you go. Here's the loop,
Oh, there
right?
you go. Nice. Yeah, yeah, yeah. Exactly. Like,
There. Here's a branch. This is a branch. This is a branch. This is a branch. I mean,
right. Like,
it's
hmm
still it's still this happening, but
yeah,
now,
and inside of there that you don't see, there's other branches and chars
yep.
because we need
Oh
to
yeah,
do
here.
UTF-8. You know, we need to turn bytes into chars, and like, I mean, if you look in
Yeah,
there, like, we need to understand what is this code point. You know, is it a surrogate pair? Is it anyway? Like all the
yeah, yeah,
UTF-8
yeah.
decoding logic.
Point to offset. Point to UTF-6. All of this unclipped. Clip. All right. Cool. So that's the background, right? We have rope data structure. Instead of just storing up to 128 bytes, there's now bit masks that serve as an index into these 100 up to 128 bytes, right?
Correct.
All right.
Correct.
So what do we want to do today?
Yeah. So there's basically like maybe yeah, I think I'm sharing my screen.
Yeah.
Like
Yep.
if you look at so I captured this profiler, this instruments profile of running
Mm-hmm.
Zed, and I think I had around like 1,000, yeah, 1,000 selections and kind of moving left and right.
Mm-hmm.
By the way, like one thing I want to say right off the bat is, yeah, I just love this tool. Instruments is like
Yeah.
one of the
Instruments is nice.
coolest pieces of software. It is buggy at times, but I don't know. I just want to give a
You
shout
also
out
said
to
that the new
work on it.
version got a lot better,
Yeah, the new
right?
version has like this flame graph, which it didn't have before. Like
That's
before, you
right.
had to do this, and I don't know if this is still as buggy as it used to be, but I'm
Yeah.
basically relying on the flame graph now, and I don't know,
That's
it's really
nice.
really nice. But anyway, like if you look at you know this profile and sort of squint, a lot of this, you know, if you look at this big rectangle over here,
Yeah.
there's this, where is it? Selection collection. There you go. Here. So here we're basically taking. I'm going to focus on the subtree. Basically taking a bunch of selections, and I think, yeah, like I said, it was 1,000 selections, and we're kind of converting them to points. So like,
Hmm.
you know, we have anchors. That's not. Yeah, you can look at what an anchor is in a previous episode of Zed Decoded. But basically, like, yeah, we turn we take these selections that are stored as anchors in the CRDT, and we translate them to points. And if you notice here, a lot of the time, like the biggest source of you know cost in here is transforming from um, a display point. I mean, it's this display point to inlay
Mm.
point, right?
Mm-hmm.
And a
Mm-hmm.
lot of it goes in this tab snapshot to fold point. So that's one piece. And I think we do the opposite here, where we turn from a point to a display point. Is
Mm.
it anchor?
It doesn't
Anyway, like
show the whole name.
yeah,
Yeah.
here we go the other direction. You can see that like we're saying to tab point. And the reason for this is that if you notice how this is implemented is we basically go like chunk by chunk. So like for every we should explain probably what these are. So what the
Yeah. So
tab point is. Yeah.
before we dive into this, just to say this, can you go back to that
Yes.
instruments? So this is not like this is a real practical thing, right? Because a selection in Z is basically where your cursor is. Like if your cursor is
Right.
somewhere on the screen, that's a selection. If you have stuff selected, the selection is not empty. If you just have your cursor somewhere, it's an empty selection. Imagine you have 50 cursors and then you want to say, I don't know, insert, I don't know, some action that modifies the text. What we do in the editor is we take all of those selections, and then most of the time you need to figure out where in that file on which line you are. So this is what we're talking about here.
Correct.
We know where the cursor is, but now we need to know where in the file is that
Right.
cursor.
And also where do we need to display it on screen? Because
Mm.
like not only, you know, if you look at like a file is just like a bunch of bytes, right? But as a user, you don't see like, you know, a sequence of characters, right, in just one row. What you see is a bunch
Yeah.
of lines. So like, and that's what the rope does. Like the rope kind of transforms this kind of sequence of bytes into like this sort of two-dimensional structure. On
Right.
top of this two-dimensional structure, Zed offers other UI features that also need to be indexed. For example, you can fold stuff, right? So you can say, I don't know if you can,
Yeah,
if
yeah.
you're looking
Here,
at my
I'm
screen, or yeah,
folding.
you can, right. So like, what that does, as you can see, like, is kind of effectively removing rows from the thing you're seeing, right? Like the kind of the net amount of rows that are displayed is shrinking,
Yeah.
right?
Yeah.
And similar thing for tabs, right? Like in a Go file, right? Like you have you use
Mm,
tabs for indentation, but you don't want to show the tab character, right? Like you want to
yes.
expand the tab to be however, I don't know what it is in Go, is it 4 byte
Whatever.
or
Yeah, 4. I think most people use
right?
4.
But so basically, like there are all these transformations and these like visual transformations that are not reflected in the buffer, but like need to be reflected in the UI. And we want to be able to say, okay, the user has, the the user selection is after this character. Okay, great. That's where it is in the buffer and the
Mm,
CRDT. But where does it end up going on screen, right? You
yes.
have wraps. That's another one. You have inlays and Rust. There's a lot going
There
on.
you
And
go. Yeah, here. Like if I jump over this inlay hint here that you see on my screen, this is not in the text file, but
right.
from the perspective of the editor, you still want to know, including the inlay hints, am I in this column? Am I in that column? Or am I in this column? And we need to count those too.
Correct.
Yeah.
So yeah, and so that's basically the responsibility of if you go like in display map and follow me into display
I want
map,
to follow.
like a display map is basically the structure that sort of aggregates all these various translation behaviors, and we have a map, and it kind of aggregates all the kind of this other individual
Mm,
indices that kind of track each of these things we just talked about. So we have an inlay map for the inlays, a fold map for the folds, a tab map for the tabs, and this is where we're gonna dive into today. A wrap map and a block map. And blocks, wrap map is for soft wrapping. I mean, here it even
yeah.
says in the
In the
comments.
comment.
So basically, so like we need to go both directions, right? Like, so from the buffer, we want to know where a certain selection ends up on screen, but then like the user can move that selection around, go left, go right, and it does so kind of visually. So like it's sort of, you're moving your selection in screen coordinates, right? So
Yeah.
after you do that, you want to go back and store it in buffer coordinates, because again, like that's the fundamental state. How that's, where that location ends up on screen is kind of like depends on the particular configuration that you currently have. If you have a
Yeah.
fold, you
Yeah.
don't have
Yeah.
a fold, etc. There's this translation going back and forth, right? Like from the buffer to display, from display to buffer. And so like if we go back to this instrument over here, like a lot of you can see here, like in this flame graph, like tab
Two tap
snapshot.
point. Yeah.
It's like going to fold point and going to tab point is taking most of the time. I think the aggregate time is like 41% plus, what is it? 38. It's like,
What did
80% of
you
the time.
do while recording the profile? Just scrolling through a file, or?
I was just moving around. I was just hitting left, left, left in like I had like
Oh,
1,000 selections, 1,000 cursors, and I was just like moving left, leftward. So basically
okay,
like
okay. So the tab translation takes up time.
right. And the reason for that
Okay.
is, if you see how this is implemented, is like we don't, like the tab app doesn't really index anything actually. Like it's not, it's a little, it's slightly different from the other maps that we've got, where like we actually store information about where each kind of transformation is. For the tab map, we never did that. Part of it is
Mm-hmm.
because like when you have like a file with lots of tabs, like it could be in Go, like that ends up being like, you would we need to store like a lot of like information saying like, okay, you have a tab here, you have a tab here, you have a tab here.
Mm.
And we didn't do it. But the problem with not doing that is that now the only way you can sort of understand how to expand that tab is by looking at the text. And so that's a problem because again, it means that we're unable to use basically any indexing. Like we don't know, like it's sort of akin to what we were looking at at the chunk level. Like every time we need to be like, okay, let's look at all the chars. Where is this? I can show you like how expand tabs works.
Oh boy, yeah.
Like for each character, we need to be like, okay, is this a tab? Okay, great. Where did this tab occur exactly? Okay, like it occurred at like 3 characters after sort of the because like tab expansion works at like with tab stops, meaning like if you know if you have a tab that starts at 0 and yet say that you have a tab size of 4, right? Like if the tab occurs at 0, like you want to expand it to be 4 bytes, right?
Yeah.
But if the tab occurs at like position 1, you want to expand it by 3. Like you just want to, like the tab sort of always wants to
Yeah.
align to a sort of this imaginary grid.
Yeah. Yeah. Yeah.
And so yeah, basically you need to know where these things occur.
So if I do we see, can I show tabs? Is this like
think I think there's a way of showing invisible in the settings probably.
yeah,
I
let me
forget.
quickly docs invisible characters.
Yeah, I think it's like there's like a show white spaces.
Yeah, how does this work?
Yeah, I think it's show white spaces all you can say.
Yeah, we can
Exactly.
let's do it real quick. Sorry, if I go in here and I say let's do it in we can do it in Rust because we're in Rust saving.
Although we won't have
There you go.
tabs there, so yeah.
Yeah, we won't have tabs, but oh yeah, right. Let's do it differently. Let's
Maybe let's
say
do it in
Go.
a Go file. Yeah, exactly.
Yep. So then here, if I say show whitespace all, and I create a new file, and I set the language to Go, and I set package main, func main, right? And I go here, there you go. So here,
Right, so like
there's a tab, and if I say if 1 plus 1 equals, 1 plus 2 equals 3, and sorry, this is my brain in 2 languages. Here, yes. So here we have 2 tabs, right?
Right.
And what you're saying is if I go here and I type in A and I hit tab, then this tab here is not expanded to 4, but it goes to the next multiple of the tab
next
width.
tab stop, exactly.
Oh, tabs are complicated.
Yeah, it's tricky.
Okay, back to tab map. Yeah, here.
Right. So imagine needing to do this like every single time, right? Like it's not great, and especially it's not great when you don't have tabs. Like, I really like this idea of like paying for the abstractions that you use, right? But right now
we're paying for this. We're counting the tabs, even though we know that in Rust there's 99.9% of the time there's not going to be tabs.
Right.
Okay.
Right. So like,
okay.
Not great, right? So sorry, let me turn off invisibles again because
it's confusing. And I mean, sorry, what was it in a tab map? The whole goal is like, why are we doing this? Just to recap this is we want to know where is the cursor, right? So if the cursor, like here, like the cursor is, I don't know what the offset is, right? But let's just say in this line 7, it's after the second character, right? It's after the A and the tab, but on a visual level, if you compare it with the func up here, it's actually after 4 characters, and that's what the tab map is supposed to figure out.
Yep. Correct. Yeah. So like if you put your cursor back into A there, here. Right? Like like the offset on that line is going to be like 2 or or where your cursor is,
Yeah,
maybe
yeah,
go right. Yeah, that's going to be 2 because you're just like after 1 byte for the A and 1 byte for the tab. But notice that in there, like we're actually at 4. Like in display coordinates, we're at offset 4 for that row.
yeah, yeah, yeah. All right.
Okay, so yeah, that's kind of the problem. And so what I think we can do here is kind of take advantage that we do have a rope, and I'm thinking about 2 things. And another caveat is that this might be a little slightly different Zed Decoded episode because we're going to be coding and to
Figuring
be
things
complete.
out.
Exactly. We're going to figure it out as we go. We have a rough idea of how it's going to work, but yeah. Yeah, you're going to be along with us for the ride. Yeah, so my thought is we could do 2 things. One thing is at the chunk level, exactly as we index new lines and other stuff, we can index tabs. So we can know exactly where a tab occurs in the chunks on each chunk. And at the rope level, we could do the same. We could say, okay, like we can store how many tabs are in a certain portion of the tree. And my thought with that is what we should be able to do at the tab map level is say, okay, like we're gonna park our cursor at the start of this row, and we're gonna have like a specialized iterator or cursor. I don't know, like it's probably gonna be a cursor, but anyway, like we're gonna have the specialized object that tells us, okay, get me to the next tab. Like tell me where the next tab is. And
Yeah,
like if there's no next tab, we're gonna pay 0. If there is, the tabs are like kind of located, they're sparse sort of. We're just going to pay the cost of sort of like, we don't need to go through each character. We could just know exactly,
yeah.
like, yeah, it's going to be basically constant once we traverse to the start of the row.
Sweet.
So yeah, and we can implement this logic again. And so my thought is like, we're gonna park ourselves at the start of the row, and we're gonna ask this iterator, give me the next tab. They're gonna give us the next tab, and we have a column that we want to expand up until. And so like we're gonna need to be like, okay, this tab occurred at position 3 or whatever. Okay, let's do the tab expansion. Now we know where we are in in tab map coordinates, and we keep doing this for every tab that we encounter. So I don't know, let's do it.
Let's do it. Yeah, yeah, yeah.
So I think, yeah, it might be nice to start from the bottom. Like we know exactly, I do think we know that we want to index the tabs at the chunk level. So maybe we could start there.
Let's do it.
And so, yeah, maybe let's create a branch, call it, I don't know, tabs, or I don't know.
Tab indexing.
Tab
right?
indexing. Great. Love it.
We just have this tab indexing. Let's do that. All right.
Love it. And so, oh wait, let's delete some of this temporary code.
I think that was it.
So yeah, my thought is we can say, yeah, tabs, similar to these new lines, tabs is like another one of these masks. And similar to this, we should be able to say basically that. And we also need to modify some of these things. Like, for example, we want to be able to append, a chunk to another, a chunk slice to another chunk. And so, once again, this is like sort of, it's a mem copy. So I guess that's linear, although that's very fast. And then we just need to say tabs, basically copy this.
Just the same, yeah. It's similar to new lines in that it's an index of a specific type of character, right?
Correct.
You could do the same for exclamation points if you're interested.
Exactly.
Or something. Yeah.
Exactly. Or, I don't know that I want to do this right now, but maybe grapheme boundaries as well. I don't know how expensive that code path is, so maybe it's fine. Right now we're doing that on the fly. But anyway, yeah. So like, we have also this other struct, which is a chunk slice. Basically, it's like a reference version of the of the chunks. Okay, so there you go.
I added here.
Nice. And then let's see. So I think we need to has slice tabs, self tabs. And then I think we'll need to do something in slice. There we go. Split at. Okay, nice.
0 here.
And I'm noticing here we're doing this comparison twice. If mid is equals to max base, if mid is equals to max base, we don't need to do that. We know at this point that that's not going to be the case, so we just do that. Okay.
Nice.
But yeah, like tabs, right, that's going to be exactly the same. Compute that mask, and we sort of say,
Here the same.
exactly, we want to, so yeah, the end kind of gives us the lower portion, and the shift gives us the higher portions of those bits, right, that we're splitting at. So that's fine. What else have we got?
Why does it
Slice.
missing?
Okay, yeah, slice is the same. And
This is
just gonna
also
go,
the same. Yeah.
yeah. Once again, like slice is similar, yeah, similar to split, but we're doing both. We're both kind of taking like kind of masking out up until the start of the range, and sort of selecting up until the end of the range. Okay, so I think,
Then
it says
here
that we're
chars.
missing. Oh, I think it's just checking. Okay,
Oh, it's done. Yeah.
are we
It
done?
was
Okay, great.
outdated.
So I mean, believe it or not, that's all we need to do.
Do
But
we need to? What about this? Chars longest row? No, doesn't
no,
matter.
that's about, yeah, I don't think that matters. All these other things are fine. I think like the thing that we will need to do is change text summary to sort of start accounting for how many tabs we've got, because the text summary is what we're going to be storing at the rope level. So
Do we need to add a test for this, or is this
I
covered
think so.
by
Yeah, I think like what
other
we're gonna
things?
do is, if you look at how we test this, this is also interesting. I think is we're gonna create these arbitrary chunks that are at most max base,
Oh
and
yeah,
we
this
sort
is
of
funny. This generates like that funny looking text where you have like the melon emoji and like characters and whatnot. Yeah.
exactly. And then for each chunk, we're gonna sort of first verify it as in its entirety, and then we slice 10 random locations within that chunk, and we sort of verify them. And when we say verify, what happens is that like we sort of do that linear, we
You
go,
compare it, yeah.
yeah, exactly. So we're like, okay, if we're basically comparing, yeah, like a reference implementation that's slower with a faster implementation that uses bit shifts and whatnot, the stuff that we just talked about. So yeah, like here we're clipping, unclipped point, blah blah blah, point row, etc., etc.
Here's
Clip point,
UTF-8.
yeah, verifying length, verifying lines, longest row. Yeah, so I think what we could do, I'm still not sure exactly like
We
what,
could count the number of ones in our tabs and compare that to the number of tabs
right,
in
we could
the.
have a method, I guess, on the chunk that tells you, like, I don't know if we need an iterator that tells you like the locations of all the tabs. That might be what we
Yeah,
need in order to implement this. So maybe let's do that. Like, and
yeah.
we're not, maybe let's test it via that. So yeah, like if we go in chunk slice, I think, so we have all these methods, right, that are like is empty, is char boundary, split at, slice, text
Text
summary,
len.
blah, 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 lines, first line chars, last line chars. I don't know. We need to pick a spot. Maybe let's put it at the end, because I think it's
Yeah,
pretty
yeah.
different from these other things.
There
This
you
is an
go.
internal method. Maybe here. Okay.
Yeah.
And for these, you'll notice I'm, yeah, basically telling the compiler to always inline this stuff, because, yeah. Yes. Okay. After, so yeah, like, I think we could just have like, you know, tabs. And my thought here is it could be basically like um, um, an iterator that tells us, I guess for tabs, what we need, look, we probably want to know like where it occurred in byte coordinates.
Yeah.
And we probably want to know like where it occurred in character coordinates. Like we want to know sort of like, because one thing I don't know if I mentioned this before, but like we don't want, when we expand tabs, we want to sort of count characters, not UTF-8 bytes. And that's for that emoji case we were talking about. Like if an emoji is like 3 bytes long, we still want to count it just as one, because that's how it's gonna, That's the amount of space it's gonna take up on screen.
Oh my god. Okay, yeah. So in my Go file, if I'm gonna put an emoji here, right?
Right.
And then I don't know, what's the fire
There's
this
one
one
that
here, the
I forget
firefighter in
which one
love.
have three.
So
Um,
then this one fills up, right? Because even though this might be more bytes, right?
right. Like if you put a tab in there, in theory, I don't know how
I
many
think
bytes
this
the firefighter is. So maybe we break in that case. What's a 3 byte emoji that? I think we have the random char iterator that tells us that.
most of the
Let's
emoji
see.
are 3 bytes.
Yeah,
Sorted by
like
size.
this emoji, like here, I'll give you. Oh yeah, if you follow me, it's like the sort of.
Yeah. Oh, these are 3 byte characters. Okay, so if
Yeah,
I
so
take
if you
that
copy one of
star,
those, yeah.
go in here, paste it, and then hit tab, and then tab. Well, I guess
We still have
it's
wait one
visually it's just bigger, right? We displayed it one, but it's just
a
I
little
think that
bit
has
bigger.
something to do with the font and whatnot because
Yeah.
that emoji is just bigger.
Yeah, so I mean, you can see here like it's not perfect, right? Like we're
Yeah, yeah, yeah.
yeah, it's sort of approximated. But yeah, I guess point being that we count the characters. We don't count the bytes.
Yep, yep, yep.
Okay, so that makes me think that yeah, basically like we probably yeah want to return the byte offset, the character offset, the character index, and the what else? Maybe just
Or
that.
just that, yeah.
Okay, great. So like maybe we could have here like a we might I don't know. Yeah, we might want to give this like an actual type because I think we'll end up storing it in other structures above this. But yeah, so let's say that we have this tabs thing, and I think tabs should store. I think you should sort of store those two things that we just talked about. So it's like it's gonna have an offset. It's
And the
gonna have
char
like
index.
a char in yeah, a char index, and also I guess we need to borrow the slice.
Its contents, like the what does it have?
Yeah, I think we can borrow the whole slice and kind of mutate it as we go, probably. I don't know. Again, this is part of the fun. Like, yeah,
Yeah, yeah, yeah.
I think we're gonna do this. But okay, so like, say that we have this tabs over here, and I guess what we're saying is like we're gonna start at offset 0, char index is gonna be 0, and the slice is gonna be self, right?
Yep.
And I guess another thing I don't know is like, do we wanna I don't
Consume it.
not consume it, more just like, oh yeah, right. Like, right? Are we taking a reference? I think chunk slice is copy. Yeah, it is copy. So I think we can consume it.
Mm-hmm.
Okay, great. So, and I guess it's complaining about this
A
because we
lifetime.
need to say that it's the same as the chunk type.
And then you
Okay.
want to implement iterator for
I
tab.
think we should be able to implement iterator. That's right. I think that's right. I guess the one thing about the iterator is that, yeah, what am I thinking about? I don't know. Yeah, like what is the item of this iterator, right? Like, I don't,
Isn't it a tuple pair of
right. Could we
offset?
have maybe like, could we say like tab position
Oh, that's good.
so that we can kind of say what each U size actually represents? So it's like, yeah, and
Yeah, that's
that, I
good.
guess. And so, yeah, tab position. And I guess for any A, we're gonna do that. Okay, and so now the fun part. I guess what we want to do is like locate where in the slice this thing is occurring. And so I think the way that we do that is by saying, okay, like we've got we sort of like we have a bunch of tabs, right? Like if we look at the slice, we're gonna say, okay, like tabs
Tabs.
And I think like if tabs is 0, I think this is our none. Like we could say,
Yep.
okay, there's nothing to do here, move on.
Yep.
Oh, and formatting is a little awkward.
Is it?
Yeah, I don't understand why it's doing that. Weird. I think
No, it's back. Yeah.
rest FMT had some issue. Okay, but anyway, like yeah, if we're 0, then yeah, we don't have anything to do. But if we're not, I think we should be able to say, hey slice, give me like your leading zeros. Leading zeros. So that tells me like how much do I need to move from the start of the slice in order to reach the next tab. So that would be like next, or
That's the
yeah.
tab offset or something. No.
Yeah, although I guess yeah, what I'd like to do is sort of like keep slicing the yeah, it is tab offset, but anyway, yeah, so tab offset, that's fine. Leading 0 is a U32. We want to make that a U size. So I guess like what we should be able to do now is say, okay, like that's where it's gonna be located. But what we want to know is like we want to do that thing again, right? Where we say like we take this, we move it by the tab offset, subtract 1, and then we ask the slice, hey slice characters, self slice dot. Wait, we have chars.
Char.
We have chars, but I think it's getting confused by this being
Yeah, underline.
yeah. Okay. So anyway, like this is sort of the mask. Let chars mask. We can sort of say that. And so basically, like this tells us, right, how many characters, right? So this would be like char count or char offset, I guess. Now, we want to sort of advance these two things. I guess like one thing I wonder about Thorsten is maybe we don't want the whole slice. Maybe all we want is those two things that we're tracking.
So we always peek into the slice at that given offset.
I think we could just say like basically just say tabs actually just we don't move in here. We don't do that. We just say like
So you also want to move the tabs as like
that's
a
right.
U? Okay.
Chars and tabs. I guess you're okay. Flip it around. Great. Because I think what we want to do next is okay. We know these things, right? So now we should be able to know that at this sort of self offset plus equal, like we advanced right by this amount, right? So this is where we are right now. This is where the character index is at right now. Sorry about that.
Anyways.
And then okay, so we've got that, and then what else? Oh,
So just so
we
if
need to
I
count the ones. Sorry, that's what we need to do. Size. Go
so
ahead.
if I have there's four bytes that are not a tab, then I have a tab, and then 4 bytes again that are not a tab, right?
Right.
This basically says the offset is 4, right? It starts here. That's a tab offset. And then and then in the chars mask, like what's the chars mask then? That's basically 0000111 like this.
A bunch of ones, exactly. So that tells us like up until that tab, how many characters can we find? And that should tell us.
Is it not? Don't we have to do it from here?
No, yeah, we're tracking it from like least significant byte to most significant bytes.
Yeah.
So
Okay,
it's kind of reversed. I don't know. I
flipped.
could have
Yeah.
gone the other way. I just felt
Doesn't matter. Yeah.
doesn't matter,
Okay,
yeah.
so then we know that the first 4 characters up to the first tab. And then what does this do? This is then the char offset. So this then gives us.
So we have this mask, and so like we're gonna have these are the chars. This is the mask, right? like if if all the chars for the entire slice were like this, right?
Yeah.
We don't want to count all the chars. We just want to count the chars up until this point. Or
Right.
sorry, up until this point. So what we
Right.
do is like mask, take this mask, end it with the chars. This is
Yeah.
gonna like activate, you know,
Okay.
just
Okay.
those bits, and then we can count them. Then we can say count ones. So that
Right.
tells us how many characters are
Okay.
there.
So we went up 4 bytes until we encountered the first tab. So that's our 4. That's the thing
Correct.
that we want to return. Like that's the one tab position we say after the fourth character, right? Or zero
Correct.
indexed. And
Correct.
then we want to say how many characters did we encounter along the way until we reach the first tab.
Correct.
Okay.
And so I think like the
Nice.
position we want to return is this. It's going to be offset self, offset char index, self char index.
Mm-hmm.
Great. But then what I think we want to do, so that's what we want to return. But now what I think we want to do is we want to say, okay, great, we did that, but we want to sort of take our chars and shift them by the tab offset +1 because we want to sort of go past it. And similar story for the tabs, right? We don't want to count them again, right? And I think that's it. But yeah, notice, right? Like here we're just gonna, like if we have no tabs, this is gonna end right away. If we have one tab, we're gonna like jump straight to it, right?
Yeah. And this, okay, so in this then takes this, say this thing, and shift it so it's just this, right? So you jump over that thing.
Correct.
You jump over the offset. Got it. Okay.
The right, so this ensures that that's gonna work. Blah blah blah. All of this I think is fine. The only thing I worry about is like this tab offset could be 63. And if that's 63, it means that we're gonna shift right by 64, which means this is gonna panic. So we might need to have like an if here that says, okay, like if we're at that point, just zero it out. But let's wait for the randomized test to tell us. Beautiful. I think that's our thing.
That's pretty sweet. Okay.
Yeah, very very soothing. I think this type of
Not if you're scared of off by 1 arrows like I am. There's a lot of zeros and ones here.
Don't be scared, Thorsten. Don't be scared. Okay. So verified chunk. I guess like one thing we could do here is basically say we could track when we verify this chunk, we could track sort of like the expected tab positions, right?
Yeah.
It could be a vec. And I think here chars, as opposed to having chars, we could, I guess we were tracking the offset, so that's fine. All right, so like we can say here, and maybe I'll do it at the end after we've done all this stuff.
So just to zoom out a little bit, instead of writing like one specific test, the strategy with this type of stuff is we just generate a bunch of random stuff and assert that invariants are true, right? Instead of saying, oh, in this case, I want the value, like if there's a tab at the end or at the start, blah, blah, blah.
Right.
Instead, we crank the random number generator and the iterations over, like fuzzing or property-based testing, right? And then you say, okay, no matter what random data I get, and I guess we kind of need to make sure there will be a tab in there. But no matter what we get, we want these invariants to hold.
Correct.
Yep.
That's correct.
All right.
And so in here, I think what we could do is say like, okay, if this character was a tab, right? Then we could go in the expected tab positions and push a tab position, which is going to be the offset, which we have, and the char index, which I think we're tracking. We need to.
I mean, char's offset is here, right? So that's the
Right. I guess we're not tracking how many characters. Are we doing that? I don't think we are. So we need to remember how many chars we've seen. So we could say like char. And maybe, I don't know, we called it char index. What do you think about calling this char offset instead? Like there's a maybe byte offset and char offset.
Yeah.
So
Yeah.
that's
Yeah.
clear what we're doing.
Yeah.
Um,
So and then you
and
want to say chars.
I think I have to, yeah, I renamed, but man, Rust Analyzer. Okay. Let me do it again. Maybe that didn't go through.
Do we?
Yeah, it's not liking it. All right, I'll just do it
Did you
manually.
just manually? What did you call it? Byte
Oh, no,
offset.
I did. Now I did it. Byte
Yeah.
offset. Yeah. I don't know. It took a while.
And then what?
I
And
didn't even do it properly. All right.
do
And
we
this
want to
should be char
rename chart?
offset.
Okay. Let's. I
You're
will do
doing
it.
it? Do it. Do
Yeah.
it. Okay. Sweet.
Then this here is now correct. This didn't. Wait,
Oh,
it
right.
didn't do this.
Because these are different. These are like
Oh,
those
these
are
are
the
on
ones that
our
we're
stuff.
tracking at the iterator level, I guess.
Okay, sweet. So now these are back.
Sweet.
All right, and then
Tabs,
here,
chars, blah 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 blah. Okay, so yeah,
chars.
where are you?
That's. I'm down here at the end of the
Right.
test.
So we can call this char offset now, right?
Yeah.
And basically, like here, can
Bumped
always
it
just
down
be plus
here.
1. Exactly. Perfect. And then this could just be that. So these are our expected tab positions. So I think this test is like less fundamental than other tests, I think. So I'm gonna put the assertion for it at the end of it, so that like other stuff fails first if things are broken. So yeah, I think we should be able to say like, we should assert that if we ask the chunk for the tabs for this thing and we collect it into a vec, this should give us the expected tab positions.
That's sweet. Do we have debug implemented on the tab
We probably
position?
need to implement it. Probably need to implement
I'll
it.
add it, I think. Oh, partial EQ.
I think both. I think it's okay to implement both. Yeah,
You mean-
EQ and partial EQ. I think in order to have EQ, you need to have partial EQ. EQ is just like a marker trait. Like it doesn't do anything in addition to partial EQ. Okay, so I think that does it. And so my expectation is that if we run this,
where was the test again? It was. I mean,
it's test random chunks. I think.
Okay, let me use my new.
Nice.
Spawn
my
nearest
expectation is that we're gonna see this panic because sometimes the tab is going to be located right at the edge of the chunk. I mean, there might be other bugs, but like if all the other bugs are, fixed or not there, I think.
Left, right. What do we see? It panicked, right? Because of the failed assertion. Byte offset is 120.
Okay.
Right is this. So we have.
Let's see. So the expected
they're completely
ones,
different. Yeah.
They're very, very different. Okay, so we must have done something wrong. Let's see. Like, so we're saying like, tab offset is the amount of tabs that we've got, and then we do that, and we plus equal that. How is that possible? I guess we need to do +1 here for what it's worth. I don't know that that matters necessarily, but like I do think that is like we kind of want to skip exactly as we're skipping this. We also want to report it. We want to skip that tab. Like next time, we don't want to report it again. But I guess I'm still a little unclear on why that's failing so spectacularly. So
hey, why is it?
I wonder, like, is there something wrong with the way that we're slicing tabs and mask? I mean, that's all the same. Okay, left failed, right failed. We should probably look at what we're doing. Like, is it like a yeah? So you should be able to enable Rust log.
Yeah. Let
So if you say
me.
Rust log info, we should be able to see exactly what the chunk is and how we are instantiating it. It must be something easy because like it's failing right at seed 0, so we're gonna figure it out.
There you go. Chunk. Oh my God, it's an emoji right away.
Sorry, yeah, the screen share is not great. Okay, there we go.
Here.
Chunk is that
Emoji.
emoji.
Carriage return. G.
Yeah, and
Tab.
what's weird
Q.
is that like we don't even have 120 bytes in here.
Yeah.
So I think we must be doing something
Yeah.
pretty wrong. And so let's think about what that is. So let's see. If we go in next, are we doing? So we're saying byte offset is that, char offset is that. We're saying tabs leading zeros. We know it's going to be a certain amount of zeros. I mean, we could also like
The
one thing that I like to
char
do.
offset is right though, right? Look. Like the first one here, we say 3. So we have 1, 2, 3, and we get the first tab, and then there's another one. So the char offsets are right.
Uh,
Oh, sorry.
I see. Yeah, the
Sorry,
problem.
sorry.
Okay, yeah, the problem is. Sorry. Yeah, the problem is that like we're not accounting for the fact that this chunk might be smaller than the full amount. So basically, like, sure, we're saying like leading zeros is whatever, but like really, what we need to do is sort of we need to min it with the
You need to cut off the leading. You need to discard the leading zeros that cannot be 1 because the char is longer, right?
Yeah, the thing I am confused about, I don't know. Let's just print line here. So if I say one thing, I did a lot for creating that PR was doing this.
Yeah.
Basically, and I guess we need to
Oh.
do 128 bit. I want to look at the tabs for this thing, and I also want to look at. So I'm gonna say like tabs. Then we're gonna have chars.
Is there something format strings in Rust can't do? That's crazy.
Right, chars, and I also want to look at just the len, I guess.
Let's do it.
Self len. Okay, great. Let's
All
see.
let's run this. Cancel language server. Oh my God, need to decrease font size. Look.
Okay. Okay, so roughly, like, do we have tabs at those locations? I think we do.
I mean, we have, sorry, this was wrong what I said before, right? Our assertions are right, I guess. So the first tab is a char offset 3, which is the byte offset 6, right? So 1, 2, 3, 4, 6, right? This. And then we have one right after that. So these two, I think, are correct, right? Like our tabs.
Right.
But
Those are
then,
right. But for some reason, we're saying, I mean, so let's see. Every time, so we're going to say dbg tab offset, I guess. What do we find out there? Because it seems like we're reporting 120, and I don't. Yeah,
where
so
did you
I
add
added
it?
a debug in the iterator.
Yeah.
I was assuming that, yeah, tab offset is going to be like,
Yep.
you know,
Wait.
what is it? 0, 1, 2, 3, 4, 5, 6, 7? Yeah.
Tab offset is 120.
Oh, sorry.
I mean, the
I'm an
leading
idiot.
zeros,
I'm
right?
an idiot. Yeah, it's
We need
trailing
the
zeros that we
trailing
want.
zeros.
Yeah, trailing. Okay.
Okay, so now, come on.
Sorry about
All
that.
passing, all passing. Look at this.
Yeah. Okay.
That's a new
We're
one.
only
It's not.
running.
It's not off by 1. I guess it's a boolean. It's the other
Yeah, it's
direction,
sort
but
of right.
all right.
Okay. Now the weird thing is that I would have expected this to not work because
The max length.
exactly. I think this has to do with the fact that sorry, where is it? Where is it? Max base. I guess for tests that's encoded to 6. let's not do that, and instead let's say that it's always 64.
Yeah. Okay, so that means we index stuff with 128, like a bit mask of 128, but in the tests, like in the tests, we switch it out and the chunks won't ever use 128, so we won't ever test those boundary cases. But now
Exactly.
you flipped it, and now if I
Right.
run it,
In theory, it's gonna panic. Let's see if I'm right about
not
that.
yet. No.
Okay,
Lens 7.
maybe let's run yeah, more iterations.
Yeah.
So
How many?
I don't know, even 100,000.
100? 100,000. Let's start with 100. Okay, I didn't do it. Thousands. No panic. I mean,
Yeah,
it's
and so
kind of the infinite monkey type thing here. Like, if you have
yeah.
if you have 100,000 monkeys, will somebody put a tab at the end of a 120 character?
I think yeah, also let's delete this. I'm gonna delete
The debug stuff.
the debug stuff. Yeah, I'm confused as to why that's not
This is what my family thinks I do all day, Antonio. Look at my screen.
yeah, like
This
the
is what I
matrix
tell them I
the
do all
matrix.
day. Yeah.
Yeah, that's interesting. Like I would have thought that yeah, like
There you go.
do we get a panic?
Attempted to shift right with overflow. You
Nice.
called it, no?
Awesome. Exactly. So I think what that means is that like
Oh,
if
there it is.
yeah, exactly. Exactly. So it took a little bit, but we
So
found
it's
it.
not infinite monkeys. It's 85,000 monkeys.
And yeah. So basically what I think we need to do here is yeah, like we want to make sure that like when this happens, when the tab offset is the max, yeah, we need to take special action there. It basically means that the mask wants to be like um, yeah, it wants to be all ones, I think. So maybe what we could say is like, right, like I don't know, it's almost like two different code paths altogether. It's like, yeah, I almost want to just say like, okay, if tab offset is max base, right? Because it's gonna be
Is it max base
100.
-1? No.
No,
No, it's
because I
max
think
base.
the uh
Or, I mean, the problem is that if you have,
drilling
say your base is
zeros.
12, or say your base is 5, right? And then you have this and 4.
Yeah, the leading zeros are always going to be like less than max base for sure. So I don't think actually sorry, it's not this is not the problem. The problem is down here. The problem is that like if the tab offset, you know, is sort of we could almost just say like what do we want to say like byte offset +1 tab I think it's this shift that's like failing actually because we're doing the +1 because the leading zero are always going to be 100, you know, in that case they're going to be 127, so that there's no problem there.
550. It's, oh no, wait a second. Did we add a line?
I just added a line. Yeah, I think it's this. Yeah, 546 I would imagine.
Wait a second. It says 550 here.
Try again because I think we had like
Yeah,
debug
we
statements.
changed. Oh, yeah,
You
yeah.
can also now fix the seed. You can say seed that and just rerun that one seed, but it's also
So
pretty
it's
fast. So whatever you want.
8560, this, right? And then there you go. 564, you're right. That's this
Great.
one.
Great. And so like what I think we should be able to do here is say like if the tab offset is actually like you know yeah, what do we want to say? Like we could almost yeah, I don't know how we want to structure it. I guess we could say if the tab offset is equal to the maximum, right? If it's kind of like the maximum -1. Another way of doing it is say like okay, like we oh go ahead.
Don't we want to say if it's the max, we want to set it to 0, so the next time
Yeah,
around?
I guess. Yeah, I think what we could say is like shift these two by one, and then we can say if the byte, like if we reached uh the maximum, which is going to be the max base, we could just say self tabs equals 0, and else we want to do this thing, and then
Yep.
we do that. So that should do it.
Now we have a branch, but yeah, I
Now
guess
we have a branch. One per tab, though, not one per character.
let's jump back here.
Okay.
All right, the tests pass.
Why
Oh,
is it
sorry.
just running? Oh.
Iterations. Sorry.
Oh yeah.
And
Yeah.
I
Exactly.
added a 0. There you go. 100,000 monkeys typing up to 128 tabs. So I want to make a SQL program. I don't know, like who taps a lot of tabs? I don't know.
I don't know. Yeah.
Oh no, sorry, SQL program is just caps lock, right?
Caps lock.
Yeah. Okay, so this looks good.
Yeah, I think this is gonna pass.
Nice.
Okay, maybe this would be a good stopping point. Let's create a commit for this,
Yes.
and maybe next time we can kind of do the next piece of it.
That sounds good. Okay, so we got. Let's just review this diff a little bit here, right? To take.
Sounds great. Yeah.
Do we need to leave this in? You want to leave this in, or how?
No. Yeah, I think let's put it back to 6. I think. Okay. As with all tests, now we feel confident that this thing is working as we think. So I think we could shift it back. And the reason for having like smaller chunks is so that in other tests, like in the rope, we can exercise more of the other code paths that don't require chunks to be that long.
All right, so you put it back, or
put it back. I think 6 is fine. Yeah.
All right, so then. Sorry, I'm peculiar with this. Here, there you go. So we added our new 128 bit wide integer number. We index now just like the new line. We set the bits that are tabbed to 1. We did all of this other stuff too when we copy or create new chunks, right? Chunk slice is when you look at a portion of the chunk. Or is it when you look at the portion?
You basically, it's like a string slice. You can kind of take a chunk and kind of shrink it.
Yeah. Then here, this was I guess accidental optimization too. Yeah. One more brand. I get maybe the compiler would have caught this.
The compiler would have caught it, but it's confusing for other people to do. I guess. I mean, it's already pretty confusing with all this shit.
All right, so then here is the entry point, right? Given that we now index in 128 slots where the tabs are, we now create an iterator with which we can iterate over the tab locations in a given chunk slice. So here the struct, tab position, and the iterator. And most of the magic, I guess, is contained here, right? In these 3 lines.
That's right, which is like, get the trailing zeros, like how many bytes do I need to skip since the start of the chunk to get to the next tab, count how many chars we've got, and that's our position of the tab, and then we keep going. Yeah.
All right. And this is the test. We now keep track of this, expected tab positions, and then at the end of the test, we make sure that this is correct. And we ran 100,000 iterations of this with 100,000 different strings, and it works. Huge success. All right, so then let's stop it for today, and then the next time we're going to use this.
Correct. We're going to go up 1 layer, index this information at the rope level, and then up 1 level integrated with the inlay map, up another level integrated with the fold map, and finally we're going to take advantage of it in the tab map to very efficiently convert from tab points to fold points and vice versa. Nice.
And in between, some benchmarking, hopefully.
Correct.
And nice graphs. All right, then, Antonio, thank you so much.
Thank you.
I'll see you the next time, I guess, and everybody else. Thank you for watching, and I'll also see you the next time.